Welcome everyone. For today's prep, we're going to be looking at solids of revolution, and in particular, how to calculate their volume. So first of all, we're going to look at what a solid of revolution is. So it's where we take a section of the XY plane and we rotate it around a fixed axis. So usually in the example we're going to do, it's the x-axis, but sometimes it's the y-axis or some other line. All right, so let's look at a picture to get an idea for what these solids of revolution look like. So we're going to start with a planar region, something that exists on the XY plane. And usually it'll be a section that's bounded in between a few curves. So that's what we're seeing here. We have this one function that's plotted, and then we're looking at this region that sits underneath the curve. Okay, so then we're going to pick a line, and in this case we're going to use the x-axis, and we're going to rotate that entire region around that line. And we call that line, we give it a special name, we call it our axis of rotation. So for this example, we're using the way this picture is drawn. Our axis of rotation is the x-axis. So what we're doing, essentially, is we're taking this entire region and we're going to imagine rotating it. So it's going to get extended into a third dimension. And when we do that, if we kind of look at the three-dimensional view, let's look over here now. So we've got our x-axis. Kind of poking out the back here is our y-axis, positive y-axis. And then we've got our new third dimension, our z-axis pointing up. And what I have graphed here, this is a surface. This is an example of a surface. It's a two-dimensional object sitting in three-dimensional space. And how we're getting this surface is we're taking this section of the curve, going back to the planar region there, we're taking this section of the curve, which is right here, and we're just rotating that around our axis of rotation. So we're going around the x-axis. So, if you kind of pick one point that sits on the curve and you rotate it around the x-axis, that one point is going to trace out a circle. And so any point that you pick is going to trace out a circle. All right, so the section of the curve is giving us kind of this outer shell, this surface, and the region inside is giving us, well, the space that's inside the surface. So our task is going to be to find the volume of that space. So enclosed by the surface. So the surface you want to think of as kind of like the outer shell, and then we're trying to find how much space, the volume, is inside of it. Okay, so how are we going to do this? Well, we want to imagine, if we go back to our planar view here, what we're going to do is we're going to slice this region up into a whole bunch of tiny little strips. And we're going to rotate each of those little strips around the axis of rotation. All right, so we're slicing our region up into these tiny little, thin little strips. And let's look at one in particular. So let's say, this one right here. So we're going to call this our cross-sectional cut. So we're going to kind of slice into our region. And we're just going to get a cross-sectional view. So here's our cross-sectional cut. And when we do this, we do it perpendicular to our axis of rotation. So in this case, it's perpendicular to the x-axis. So let's look at this one cross-section on our graph here, on our three-dimensional graph. So what did I do? Kind of picked it in between 1 and 2. So let's again kind of pick it in between 1 and 2. And I think maybe like right here. So we draw our little cross-sectional cut. And we imagine, again, rotating this around the x-axis. So if you imagine that kind of rotating, what happens is it's going to trace out a circle. And that's going to be our cross-sectional area, our cross-sectional region. So, and that cross-sectional cut that we drew, that initial one from our planar region here, we cut into our region perpendicular to the x-axis. Well, our cross-sectional view in 3 dimensions is a circle, and that cut that we made is actually the radius of our circle. So the 3D cross-section is a circle. And the radius is, well, that original cut that we made. Okay. So the idea then of how to find the volume is we're taking our 3-dimensional object and we're going to, like I said, we're going to slice it up into a whole bunch of these little thin strips. Now, when we translate that over to our 3-dimensional view, what we're doing is we're taking our 3-dimensional object and we're going to slice it up into a whole bunch of these little kind of like wafers or discs. And each of these wafers is going to be really thin. So we're making these cuts. The width of these cuts is going to be really thin. So we're making them thin, and they're all going to be circles. And so how we then we're going to have all these little thin strips. And how do we put that all together to get the volume? Well, we have our integral formula. I guess that would have been more dramatic if I was out of the way. We have our integral formula. There we go. So if we're trying to find the volume for a solid of revolution, where our region goes from x equals a to x equals b, what we're going to do is we're going to find the area of our cross-section. So a of x represents the area for our cross-sectional cut. That's perpendicular to our x-axis. And in the example that we saw, our cross-sectional cut was a disc. So something like this. And the center point there for our cross-sectional view, the center point, that's our axis of rotation. All right, so again, what we're doing is we're slicing up our 3-dimensional region, our 3-dimensional solid, into a whole bunch of these little discs. And so the idea is there's a small thickness here. They're very thin, but there is a thickness. So that's what dx represents. This represents the thickness. And the area then, when we multiply it with the thickness, is giving us the volume. So what we're doing here, a of x times dx times that differential dx, is giving us the volume for each of those tiny individual little discs. And the integration is essentially adding them all together. So remember, when we first introduced the definite integral back in Calc 1, the definite integral is kind of like a fancy way to add a whole bunch of tiny things together. So We're slicing up our three-dimensional object into a whole bunch of these tiny, thin disks. A of x times dx is the volume for each of them. And then when we integrate from A all the way to B, we're essentially adding up all of those little volumes to get the total volume. All right. So how are we actually going to do this, though? So far, it's all theoretical. How do we actually do this? Well, for these solids of revolution, we're rotating around an axis of rotation. So there's always going to be a center point, and all of our kind of objects all of these cross sections are going to be related to a circle. So it's important to remember area of a circle. Well, what is it? So area of a circle is pi times the radius of that circle squared. And this is usually going to be our area function that we use here. And if we remember, what was that radius? Well, if we go back, the radius was the length of this segment here, where we go from our axis of rotation up to our actual curve. So the height of our curve is actually going to tell us what the radius is for each of our cross-sectional cuts. All right, so there is another case, which we'll look at later, where we still might end up with a disk, but we drill a hole through the middle. And we're going to call that a washer, but we'll look at that in a little bit later. So let's try one example. Let's look at example 1. And we're going to find the volume for the solid obtained by revolving that region around the x-axis. So this is, if I get out of the way for a second, this is the region that we've been talking about. So it's underneath this curve, and we're going from x equals 0 to x equals 2. So again, we're taking that region and we're going around our x-axis. So let's see how to actually do it. So the first step is we want to draw our cross-sectional cut. We've kind of already done that for this particular one, but usually if it's a fresh problem, this is something that we want to do. So get completely out of the way here. So we have our region. We identify our axis of rotation again. So in this case, our axis of rotation, just like in the picture, we're going around the x-axis. So we're going to go around our x-axis here as well. So our first cross-sectional cut here is we're going to do this perpendicular to the x-axis. So when we draw our cross-sectional cut, we want to do this perpendicular to axis of rotation. So whatever your axis of rotation is, you want that initial cross-sectional cut to be perpendicular to it. All right, so then we want to find, so just get that done. So in this case, we're going from our axis of rotation and we're cutting all the way through to the curve. Just cutting all the way into this thing. All right. And I guess I can come back now. All right. So then step 2. You want to figure out what the radius is. So as we mentioned, the radius is, well, just the length of this segment here, where we go from our axis of rotation up to the actual curve. So this is our radius. All right, so, well, what do we have here? We're looking at a line segment here that's vertical. So when we talk about vertical distance, we talk about vertical, what we're really talking about is the y-axis. So vertical tells us that our radius here is going to be equal to y. So our R value, the radius of our cross-sectional cut, is going to be y. And we know it's y because we're looking at a vertical line segment. Well, we just so happen to know what y is actually equal to. So y is equal to in this case, it's an exponential function, e raised to the x over 2. Okay. So this function, the graph that we have here, is telling us, any point on this curve is telling us what the radius is for that particular x value. So if we find a particular x value and then we look at the corresponding point on the curve, well, that distance there, that vertical distance, is the radius of our cross-sectional cut, and that vertical distance is the value of this exponential function. So once we've identified the radius, then we're ready to figure out our area function. All right, so our area, in this case, we're looking at just a disk, so it's pi r squared. And if we fill in what our radius is, the r value is the value of our function, so e raised to the x over 2, and we're squaring that. And when we have multiple exponents like this, so we have the number e raised to a power, and then that whole thing raised to a power, we can simplify this. So we just multiply the exponents. So this ends up just being pi times e to the x. And so once we have that area function, now this is where we do the integration. So step 4 is to integrate. And this is going to give us the volume. All right, so our volume here is going to be the integral from 0 to 2 of our area function. And if we fill in our area function here, we found it to be pi times e to the x. So we're going to integrate from 0 to 2 of pi times e to the x. And this is a nice, easy function to integrate. So the antiderivative, just pi e to the x. We're going to evaluate this from x equals 0 to x equals 2. And then we plug in. So we end up with pi e squared minus pi e to the 0, which simplifies to just pi e squared minus pi. And when we do these, the volume we get here, if we've done everything correct, the volume should be positive because we're expecting, we have a solid object, we expect the volume to be positive. All right, so we're going to try more of these examples in class, but this is just to kind of get a little taste for what we're going to be doing. So we'll see you then. Bye-bye.